Hi guys, today I'm going to be discussing Prim's algorithm for finding the minimum spanning tree in a graph. And so, to get started, what a graph is going to be a list or a representation with weights between the edges of how much it will take to cross that path. And so we have these vertexes, the edges, the weights that are corresponding to the edges, and then we have loops and parallel edges, so on and so forth. And so, what we're looking for here is we're going to try and find the minimum spanning of this graph, which means the minimum path to go to every single vertex compared to other graphs. So we're going to have many different variations. So like this right here is a spanning tree of this graph. And so that's just going to be one possibility of something that we can take to go on this. And now this right here, we go from A to D, D to B, B to E, so on and so forth. But we could have A to C, A to F, or C to F, so on and so forth, and we'll have many different combinations. So how this works is this spanning tree is going to go from A to D, and that's going to cost 6, because that's the weight corresponding to that edge. Now D to B is going to cost 3, and so we're going to go A to D, D to B, and then now we're going to go to E, costing 1, keep adding it up. So how we find our overall weight, so our solution, is going to be by adding each of these weights up after we have found the entire thing. And so this is going to cost 29, which may be expensive, may be cheap, who knows, but we need a solution or an algorithm to find out what the minimum is so we can find our cheapest possible route. Now that's where Prims comes into play. Prims is going to be finding us that minimum path right there, and where we can choose to take the cheapest option and save money, save whatever your cost is. So how Prim's algorithm works is you're going to start out, so your first step is to get rid of all loops. So right here, this is what it means by a loop. So A is going to come back to itself, so we get rid of that. So the second step is to get rid of all parallel edges. Okay, so what that means is like this right here. That's a parallel edge, so we would get rid of that. Now the third step is where we're going to create our solution set. Now the solution set is going to contain all of our answers in the order that we're traveling to them. And so you'll start out A, then go to B, then go to C, whatever your choice or your cheapest path is. That's what that's going to contain. So we're going to call that VT. So we're going to create V sub T. And then that's going to be empty to start out. Now the fourth step is you're going to create your MST solution. So your MST solution is going to be your more descriptive version of your solution, excuse me, which contains your A to B, what you're traveling on, and also the weight that corresponds to that. And so we're going to create MST, and we're going to sub that ET. So ET is just going to be empty for right now. All right, and so that's all the setup. Now I have to do the reoccurring step, the recursive part. And so we're going to have, you have to start at one edge, and then you're going to look at all of the edges that are not, or that are in V minus VT. So I forgot to say, V is going to be all of your vertexes. So A, B, C, D, E, F, G in this case. And so B, C, D. So that would be our V right there. And so this one, you're going to find something that is not in V minus VT. And so you'll understand a little bit more, but pretty much it's saying we can only go to a node that we have not already been to. So, we're going to find the cheapest path of our options in V minus VT. So we'll have multiple edges, and we're going to choose the cheapest one, and that's how we find our minimum spanning tree. All right, so now we have this example right here, and I'll go through it step by step. And so we're gonna have our first step, get rid of the loops. So right here, this loop that I showed you, we'll get rid of that, and then get rid of the parallel edges. So get rid of this one, and then now we're ready to get going. So we have to create VT. So I'll just write it up here, VT, and I'll leave it open for now. And now we're going to create our ET right below it. And leave that open for now as well. All right, and so now we're ready to go into the recursive part. So we're going to choose to start at A and go in alphabetical order. So we're going to add A to our solutions. And so now we're right here. Now, the recursive part is we're going to find the cheapest path in V minus VT. So we have V minus VT, so it's going to give us everything but A. So B, C, D, E, F, G. All right, so we can go to any of those nodes, which is any of our options right now. Now I can go here, which is 5, to D, which is 6, or to B, which is 4. Now the cheapest option of all of those is going to be B, which is 4. So we're going to choose to go there. So we're going to go to B, and then we're going to add that to our solution set, and now we have to add it to our MST solution as well. So we're going to go smaller parentheses, A to B, and then how much it costed. So it costed 4, we're going to add it right here. All right, so that's where you're coming from, that's where you're going, and that's your cost for it. So from B, we're going to now go to the recursive part again. So you're going to pick the cheapest option and V minus VT. So V minus VT now has everything but A and B. So we have C, D, E, F, G. So pretty much how you're going to start getting this now is we have A, D, and E options right now. But A is not in V minus VT, so we can't do that one. But we still have D and E. E is going to be 1, so that's going to be cheapest, and we're going to choose to go there next. So we're going to add E to our solution set, and then add it right here in our MST solution. So B to E with a cost of 1. All right, so now E, keep going. The cheapest one here, 7, 5, 1. Can't go 1 because it's not in V minus VT. So our next best option is 5. So we're gonna go to D and add that to our MST solution as well. So E to D with cost of 5. And now we're at D, and so we have options to go to every single vertex, but we have to look at V minus VT. So if we didn't take that into account, we'd be choosing this 3 right here and going back to B, but we can't go there since we already been there. So basically, that's crossed out, and that's crossed out. So we can choose 4, 6, or 8. Now 4 is going to be our cheapest option right here. So we're going to add G to it, the solution set, G, and then going to visit. We're going to go D to G with a cost of 4. All right, now G, we only have one option because we already visited these two. It's 3, so we're going to add that one to it. Adding F to our solution set, and then we're going to go from G to F with a weight of 3. All right, so now the last one, the only option left is go to C with an option of 9. Not desirable, but we're going to have to take it. So we'll go from F to C with a weight of 9. So how I said we're going to calculate our total weight is we're going to look at our MST solution. That has all of our weights right here. And so we're going to add it up. So 4 plus 1 is 5, 5 plus 5 is 10, 10 plus 4 is 14, 14 plus 3 is 17, 17 plus 9 is 26. So our lowest weight for our minimum spanning tree is going to be 26. And so that's going to be cheaper than this 29 example. And so that's why we need an algorithm to go over all of this. All right, so now we need to talk about the time efficiency. So the time efficiency in this class is going to depend on what kind of structure you're using. If you're going to use a minimum heap, your space efficiency, or yes, your time efficiency is going to be O log, or not O log, O of the absolute value of V squared. So that's going to be your number of vertexes squared, and that'll be your time efficiency. Now, if you have a you use a minimum spanning heap, or no. If you're using a matrix and a priority cube, you're going to get that. But if you're using a minimum spanning heap, you're going to get big theta of absolute value of E log of absolute value of V. So you're going to get the number of edges times the log of the absolute value of E. Now your space efficiency, depending on which one of those you're going to choose, is going to be the same. Because they're both linear, your space efficiency is going to be big O of N. Thank you.